Hi everyone. So for this video, we're going to be focusing on some of the equations that we can use to help us to equate some of these changes in gas variables. And so I wanted to start off with the first law, which we've explored already. It's called Boyle's law, and this is the relationship between the pressure and volume of a gas. So the pressure of a gas sample depends in part on its volume, and if the temperature and the amount of gas are constant, the pressure of a gas sample increases for a decrease in volume and decreases for an increase in volume. So simply put, these are inversely proportional. And again, if we remember back to the kinetic molecular theory, if I push down, I've now got a larger weight on top of this piston. If I push down on this sample of gas, I'm going to force it into a smaller volume. The other way to think about that is that we have the same number of gases that are moving at the same speed or temperature. And so if they're now occupying a smaller amount of space, they're going to bounce off the walls of this container way more often. And the number of collisions with the walls of that container is what we equate to the pressure. So here our volume decreased by half and our pressure doubled. So there's a certain equation that gives us this inverse relationship. And so for this practice problem, we say that a cylinder is equipped with a movable piston and it's applied a pressure of 4 atmospheres at a volume of 6 liters. What would the volume of the cylinder be if the pressure decreased down to 1 atmosphere? So if we're given our volume and our initial and final pressure, we're going to use this equation here, which is the Boyle's law equation that states the initial pressure, or the first pressure, times the initial volume is equal to the final pressure times the final volume. And we've got P1, V1, P2, so all we have to do is plug in and solve for V2. Right, so this gives us our solution map. They go the extra step to show you how you would rearrange the equation so that all your numbers that you're going to equate are on one side. I don't really require that you do this, but this is just something that the textbook does to show you that we can get V2 by itself. All right, but what we're going to do is plug in our volume at 6 liters, our initial pressure at 4, our final pressure at 1, and then solve all of the numerical side to that equation to leave V2 by itself to be 24 liters. All right, one thing I do want to point out is that they do this to indicate that the units should be the same for your pressure before and after so that they will ultimately cancel out. And the volume unit that you put in initially is the volume unit that your final volume will be. So this was initially measured in liters, so your final volume should be in liters. All right, so there's another individual gas law that we're going to talk about called Charles' law, and this is a relationship between volume and temperature. And heating the air in a balloon makes it expand, which is according to Charles' law. And as the volume occupied by that hot air increases, ultimately its density decreases, which is why a hot air balloon is a method of travel, because we can heat up the air inside the balloon, decreasing its density compared to its surroundings, causing it to float. So as temperature increases, the volume of that gas, if it's in a flexible container, will also increase. So here is a numerical relationship that shows that as our temperature climbs, our volume continues to go up, but ultimately we have to reach a stopping point because there's no way that we can reach our coldest possible temperature, which is negative 273 right here, and get to a volume of 0. All right, it's technically impossible because the gas particles themselves do take up some volume. This is a nice visual where we just talk about how a balloon would change its shape. Again, the volume of these gas particles in a very cold ice water bath, those particles are going to slow down. They're going to move less often. They're going to strike the walls of that balloon less often, which means that their volume's going to decrease. But here, this is actually illustrating that it says the external pressure remains constant. So we are talking about pressure and the number of particles remaining constant. So the outside air striking on the walls of the balloon is the same in the ice water bath and in the boiling water bath. But with the ice water bath, the internal particles don't strike as much. So the external particles striking on that balloon are greater, which is what causes the volume to go down. Here, with the boiling water bath, these particles are moving way more faster and they're striking the inside of the balloon with more force than that similar external pressure compared to this balloon. And therefore, if the forces inside are greater, it's going to cause the balloon to expand to a larger volume. So Charles' law is very much a proportional relationship. As temperature goes up, volume should go up. So for this individual equation, we can just use a proportion. The initial volume over the initial temperature is equal to the final volume over the final temperature if the pressure and the amount of gas are remaining constant. And remember, all of these temperatures have to be in kelvins. So the reason we use Kelvin is because we can have temperatures that are down in the negatives. We don't want a negative T1 to be multiplied over to give us a negative V2. We can't ever get a negative volume. So if we were given a sample of gas that takes up 2.8 liters of space at some unknown temperature, and it says that when the sample is submerged in an ice water bath and the temperature is 0 Celsius, its volume goes down to 2.57. What was the initial temperature in Kelvin and in Celsius? So we're solving for T1, or more importantly, we're solving for the T1 when the volume was 2.8. So we've got V1, V2, T2. All we need to do is use our proportion to solve for T1. Again, the textbook goes the extra step to get T1 by itself. As long as you plug in the three numbers that were provided into this proportion, all you have to do is cross multiply to solve for T1. All right, our T2 was 0 Celsius, so we have to call that 273 Kelvin. And our volumes have to be in the same unit so that they'll ultimately cancel out. And we wind up having our initial temperature at 297. All right, so I want to jump back to that first slide. All right, our final temperature we said was 273 at this smaller volume of 2.57. And if our larger volume was 2.8, then our T1 should be larger. And so we go from 273 to 297. So that warmer temperature with the larger volume was 297 Kelvin or 24 degrees Celsius. Now we've got this other law that allows us to combine the two previous laws together. And we've got this inverse relationship for our pressure and our volume. And we've got this direct relationship, this proportional relationship between volume and temperature. So the reason that we do this is because we aren't always able to keep two variables constant when we're working with gases. So what if two of these variables change? We have to use this, it's called the combined gas law. If our initial pressure and our initial volume changes at constant temperature, we're going to see how that affects the final pressure or the final volume. All right, so we've got one more example problem. Here it says a sample of gas has an initial volume, V1, of 158 milliliters at a pressure of 735 millimeters of mercury and at a temperature of 34 Celsius. If that gas is now compressed to a smaller volume and it's heated up to 85 degrees, what is the final pressure in millimeters of mercury? So before we jump into the math, let's just think about this. If we're forcing the gas into a smaller volume, those particles are in a smaller amount of space, so they're going to strike the walls of their container more, which means pressure should increase. And we're heating up the particles. They're moving faster, so they're going to strike the walls of the container with more force, also causing the pressure to increase. So if our initial pressure was 735, our final pressure should be something greater than that. If it isn't, then we might have made a math mistake throughout our process. Right? So again, we've got this combined gas law, and the textbook rearranges because we're solving for P2 by itself, but we're given all five of these variables except for P2. So we can plug all these things in and then use just a really big proportion cross multiplication to solve for P2. But if you do rearrange P2 by itself, we'd have to multiply T2 into the numerator, divide V2 into the denominator, and this is what it would look like rearranged for P2. We still have to correct our temperatures into Kelvin, even though they're both positive. All right, so we're going from 307 Kelvin to 358 Kelvin. And then if we plug in our initial pressure, our initial and final volume, we wind up getting, with three significant figures, a final pressure of 1.25 times 10 to the third, or 1,250 millimeters of mercury. Again, we said it should increase, and so going from 735 to 1,250 is definitely an increase in pressure.